you to the webinar today, where I'm going to look at the data of an application that is running on an embedded system, or to be more specifically on a microcontroller. I'd like to show you some of the features for debugging and visualizing the data in the UDE debugger. Some of them may be familiar with you, and the others may be new. So I hope you will have one or another light bulb moment. Okay, then let's get started. Before I jump to the debugger, there is a question that I'd like to answer. And the question is, what are the data in the application? So obviously, by data, we mean all the variables, the arrays, and also structures in the application. These data can represent the state of the application. They can be the basis for calculations, or in variables, we store the results of calculations. We distinguish between data that is stored in memory. They are static and global variables, or we have local variables or local data. Our local data have no fixed memory locations. So that means they are volatile. So in the debugging tool or during debugging, we can only see them when the application is stopped and the variable are within the current scope. So local variables are either stored in a register or they are on the stack. So in fact, the concept of variables, arrays, or structures is only an abstraction at the programming language level. Seen from the hardware, they are basically memory locations or registers. And for this reason, the used variables, arrays, and structures are only part of the simple information, or not only they are part of the simple information that the compiler provides to the debug tool, so that the debugger can interpret the memory in a meaningful way. Then we have the memory itself. So this is the big storage for the data. And yeah, if you look at the memory, you need to interpret the values that you see by yourself, or the application has to do that. Data is also used to transfer information. A typical example is a function call where you have the parameters that are used to provide the data to the called functions. And yeah, that's all that are the typical ways we look to the data in software. But there is something else, especially in embedded systems or in microcontroller applications. We also need to handle the peripherals, so modules that are communicated to the outside, for example, interface modules, or to calculate data on a specific way, and so on. And for these, we have registers. Peripheral registers, or sometimes they are also called special function registers. These represent the status, or are used to control the functions of the peripheral modules, or are used to exchange data between, for example, the cores and the peripheral modules. The peripheral registers are typically divided by bit fields into with different width. So there is a need to carefully interpret the complete register value with the meaning of the bit fields in mind, to understand what the register is doing, or what the meaning of the register is. And last but not least, and this is not that is not application specific or hardware specific, you can use data to do calculations by yourself in the debug tool. I will show you that later. So UDE provides so-called expressions for that. With these expressions, you can do calculations in the debug tool based on variables or based on peripheral registers or memory locations and so on. And the fact is that they do not change the runtime behavior of the application, but it makes sometimes debugging more easier. Okay, then let's see how we can debug data or with data and in UDE and how to visualize the data in UDE. For that, I have written a small example application based on an Infineon AURIX TC3. So everything I'd like to show you in a minute is running on a real microcontroller that I have on my desktop. And that is what you see here. So that is the hardware setup that I have on my desk here. We are using a UAD 2 Pro device from our Universal Access device family to get access via the DAP interface to the Infineon triboard with the TC39. And the hardware, debugger hardware, the access device is connected using USB to my PC. Okay, then let's jump to the debug tool and prepare a debug session with the application that I have wrote in the last few days. So I create a new workspace for that. We need to tell the debugger a name, for example, TC39X. It's a B step. So then we need to specify so-called target configuration, which handles or which contains all the information that the debugger needs to connect to the triboard or to other devices. We have an Infineon TC39 starter kit, not B step, not A step, B step. We connect using the DAP interface. We save this file and we can select this. And then we want to debug only the main course, so we can leave it in the default here. I go very quickly through that. There are webinars available which explains it a little bit more, so you can look at these webinars which are available on the Hitex YouTube channel. Okay, then we have connected to our AURIX device and we can load the application. Which is an ELF file, and I load this into all the 6 cores. So the core 0 is the only one which is active on the reset state. The others are inactive. So I use the core 0 for programming the application. It is not a application for the flash memory. It is loaded into the RAM. So if I press OK, then no flash tool gets opened. Okay, that is our application, and I start the application. And the first thing I'd like to do is to look at some of the variables and some of the data structures. So I open the watch window, put it on the right side here, and then browse for some of the data. For example, I have a func enable structure here, and then also a global structure called g_app data. Func enable allows me to enable or disable some functionality in my application, and in the g_app data we have some storage for specific application data. Next thing is I'd like to enable the periodic refresh of the watch window, that we have a runtime refresh of all the values here. You see we calculate some sine, some values with a sine and a cosine function. So we see that the application is running right now. Then we can also enable some other columns here in the watch window, for example, an address column showing you the address in the memory for the variables, or you can add, for example, a maximum calculation of the values. You see, for example, the sine function has a values range of 4,000 to 6,000. There may be a meaning for that in that case, but that is for the moment not of any interest for us. Okay, looks quite good. So we can now enable another function, for example, this FFT function here, which does a FFT, press on, and then it is working in the background. We does not see anything, but we see that the values range of our sine function has been changed. Now we have a range from 0 to 6,000, and this is not okay. So it seems that something is wrong with the FFT, because once it was off, everything was fine. Once I enabled this FFT, we got a wrong value here. And we can visualize what happens for the sine variable. For that, to make it more convenient, I use the add as new entry to add a new expression based on the sine variable element of our structure here. And with that, I open the time value chart. I'll put it down here, and I want to display this sine value. I type in a name. Also for the y-axis, it's automatically filled here, but you can change that if you want. And then I browse for a variable, or I can browse for an expression, which we have here. And then I press OK. Then we can change the sampling period. The minimum sampling period is 1 millisecond here. And then we can look at our graph, and we see we can change also the x-axis to be a floating axis for 2 seconds here. Then we see our graph, and we see sometimes we have such a peak here down to 0. And now we want to have a look why does this is happening. A good idea is to use a breakpoint, for example, to break at the right axis to the sine variable. I add break on right, but you see right now, unfortunately, that is not that what I want to expect. That this is a very seldom case that I got the typical case is that you hit the breakpoint, for example, in this update function, because this is the calculation for the sine, and you see that we write here the sine variable with the sine value, with the calculated value. Okay, what we have seen already, but what I want to see to find the bug is to break at the code which overrides the sign variable, which is not this piece of code. It may be another code. And for that, I can change the breakpoint. I open the breakpoints window, put it down here and change the breakpoint and provide a breakpoint condition that hits the breakpoint only if the sign variable is written with 0. And then I can start the application again. You see right now on the diagram here, also on the watch window, that with that breakpoint and with that condition, the application is slowed down a lot because we break technically every time we have a write access to the variable. Then we have to check, calculate the condition, and then we decide if we have to continue or keep the application in the hold state. And right now we have here our break, which are caused by the write access to the design value and write the value 0. And if you look at this code, then we are not at the right at the moment because we have some latency in the breakpoint. But if you look at the code, then maybe this could be the root cause for the illegal write access. Because if you look at the structure, then we see that the FFT out error here ends at the address right before the sign value. And this looks like a kind of buffer overflow. And if you look at the for loop here, then we see that we have right now K with 512, which is a illegal index for the FFT out array. And if you look carefully here, then we see that we have a wrong comparison made with the index variable of the for loop. So the right one would be only a less than, not a less than equal. So that's why we go to our code, go to the FFT function and look for the code somewhere here and correct that. Save it, and then we can compile it again. Okay. Then once we compile the application again, then UDE asks to reload the application. We do this. We disable the breakpoint, and then we can start the application. We see right now our sign graph here. We also see the values here for the minimum and the maximum, and then we enable the FFT once again, and we see we have fixed this bug. Okay. Before I come to the next bug in our application, I'd like to show you some features to visualize data. We have here, for example, this FFT out and also this FFT in array here. FFT in is a array of structures of a tuple of xi and xr. And I want to show you how to visualize such kinds of structures and such kinds of arrays here. For that, we have a different diagram type here in UDE, which is the array chart. And for that, I use also the nice feature of the expressions. define a new signals, for example, the FFT in, and I can now browse for the FFT in, and then I have to specify a index variable, for example, $U. Dollar is important. The letter here is, can use any letter you want. And this is wrong because we have a XR to be added here. And then we can say we want to loop from index 0 to 511. And then we see here the input vector of our FFT function. We can also enable a periodic refresh. And then we see the changes of our input signal here. We can also add the FFT out, and we want to use the same axis for the Y for the x-axis. That was not wrong. That was, so we use for the x-axis there, and then we add the expression for the FFT out. Also, we use a index variable, and then we see nothing because we need to change the data a little bit. And then we change the color. Oh, I don't know why we don't see. Okay, I know, because the y-axis is not correct. Okay, but I don't like to fix this right now because we would run out of time. Okay, that's another possibility to visualize data. We can also look into the memory, of course. For example, for the input vector here, and we can also enable periodic refresh, that we can see the changes here of the memory. And when I have when I use the stop the application, then I can show you also the possibility to write values directly into the memory, into the target here. And you see, because I have enabled the periodic refresh also for the halted state, that we see the changes that I made here in the memory window, also in the diagram. Okay, so let's get back to the application. Okay, we have right now, if you look into our code, only used a Y1 loop and do periodically trigger the calculations. But in a typically embedded application, we have very often a timer which by interrupt triggers the application. And I want to use also the timer right now. I have prepared that and can enable this timer interrupt right now. And then I see that something is not okay. So it seems that the timer is not working as expected. So all the calculations are stopped here. And I'd like to show you how to debug such a case where we have a kind of configuration of a peripheral or a timer or an interrupt or something like that. And typically, timer interrupts or things like that are configured using registers, using peripheral registers. And the first thing I'd like to look at is the control register of the service request for the timer interrupt. So I open the peripheral registers window and browse for the register, which is called the SCR-STM, not SCR, SRC, STM0, which is that one. So you see this is the register to control the timer interrupt. I change the layout to 2-bit fields that we have more space to see. Okay, and when we look at this register, then we see that we have obviously two problems here. First of the problems is the type of the service request is DMA, which should be CPU 0. And the second one is that the service request at all is disabled. Okay, then let's change the values of the register. We can do this directly here in the window. And for that, I'd like to change the bit fields one by one. And then after I have finished that, I want to write the value, the new value of the register to the drive core, to the hardware. By default, the write to a register is write through. That means once I change the value, then immediately the new value is written. So I need to change, or I'd like to change the behavior and uncheck the write through option here. Then I get these two icons here, or buttons here, and then I can change the type of service as well as the service request disable enable. And then I write this, and yeah, immediately our timer interrupt seems to work again. Okay, what is the problem? For that, I break the application and reset the application, and I'd like to add the data breakpoint as write to access, and then I start the application again, and then we see that once we write to the control register, we stop. And we look to the code, and we see, okay, type of service request is written. Also the priority is written, which is the SRPM bit field. But what is missing? Missing is the enable, which is, if you look here, bit 11, bit 10, I would say bit 10. Bit 10, okay. So bit 10 is missing here. Okay, and then the type of service is also wrong. For that, we look a little bit up and see, okay, we write with TOS with core ID, with the core ID. Okay, here in this switch, the break is missing. Okay, that should be the second bug here in this code. So I change to the code, go to the init function and change it. We add the break and we add also the one at the enable bit field. Okay, should be good. Okay, here that would be nice if you have this such kind of correction command in your code. Would make life much more easier. Okay, we save that, we compile the code, and then we reload the application, disable the breakpoint and start the application, and then enable the timer interrupt, and it's working. Okay. That is very nice. We can also add some other registers here in the peripheral registers window. Most importantly, we have all the bit fields available. You have for all the bit fields also by a drop-down menu the values that are valid for the bit fields, and you can change the register or look into the registers. You can also use the registers as an expression. For example, I have a peripheral GPIO register which controls the LEDs on my board. If you look at this, we see I forgot the enable refresh. We see some of the bits are changing and controls the LEDs here. And we can add also a register here into the watch window by typing in SFR double colon P33 out. We see the value. We can change this to the hex value. And if you look, if you want to look only on one bit, then it's quite simple. You can shift, for example, by 7 mask with 1, and then you see only the 7th bit of the register here. And so you can calculate values based on expressions here. Okay. If we have, for example, a very fast running signal, for example, a sine, I like to add another watch window for the core 1. That is very fast running. Then you get a problem with the normal debug functionality. Okay, we look at to start periodic refresh, and you see it's very fast running. We can also look at the graph for that. I open a new time value chart for that. Browse in the news signal here. Then you see that we have not very nice, we see the curve is not very nice plotted. We can also change the timing and also zooming in here, and you see that's not really a sine function here that we see, because it is the frequency is too high for our sampling period. For such a case, it is useful to use trace. We can enable, for example, or we can do a data trace using the trace function in the watch window. And we open a new window which prints out or which shows a data trace of a data or a trace or a variable trace based on trace data. It took a while to calculate this, and then we can, for example, zoom in, and we see now it's a very nice function here that we print out. So if the variables or the data changes too fast, then the normal debug functionalities come to their limits, and then trace would be a good choice. And also, if we look back, or we go back to the first bug that we had, which was the buffer overflow, then you saw that with the breakpoint that we used with the condition, we have a clear influence on the runtime behavior caused by the debug tool. And also this influence can be avoided using trace. And this is the last thing I'd like to show you right now. I go back to my source code. I'll go back to the FFT function and put the arrow back. Okay. Then we start the application again and enable the FFT, and now we have the the same problem as at the beginning, and we want to debug this problem using trace. For that, I'd like to show you how to do this on the Infineon controller with the MCDS trace. So this is the trace configuration tool. Put it out. This is the trace configuration of our data trace that we have generated from the watch window. So I don't need this anymore. So I clear this. And to observe the behavior or find the root cause for the override of our sign variable, I need to create a new trace configuration task. The first is this block that I dropped, drag and dropped from the library functions here on the left side. And I change a little bit here the behavior of this block. Trigger means basically when the trace has to be started or stopped. In our case, we want to stop the trace at a certain condition, so I use the post trigger mode. We are on core 0, that's okay, and I want to see all the executed instructions to make it more visible what I would like to show. So I use the sync mode here in that case. And then we want to look at the sign variable. We have already the expression here. And then we want to specify, or we need to specify when not to trigger, which is the when we are in the calculation function for the sign value. So I use a range block for code ranges. The calculation function is the calc update function. And I specify a range. Okay, so we want to stop the trace if we are writing to the sign value, but we are not in range. So we are using action condition block, sign and not in range. So we trigger the trace on that specific condition. Otherwise, we want to write or want to trace the data for the sign variable. So we save the address and also the data, and we want to do a complete data trace. Okay, and that's all. Then we can open the trace window as well. This is also the old data from before. We clear that, and we can now start the trace recording. We have some errors here because of misspelling here. Okay, restart the trace. Okay, trace is automatically stopped, and we go to the trigger condition or the trigger, and we see our write access here to the sign value. And if we look a little bit upwards, then we see here a write or a store so where is my trace window here? This store. Okay, and we see this is the buffer overflow that we want to debug, and we see the same function as before. Okay, time is up, unfortunately. So I'd like to end this webinar feedback. Thank you very much.